on the queues. We said that this time, since we have become very familiar with linked list based implementations, we'll use arrays to implement queues. Because there are some challenges which come up in the array based implementation rather than the which do not occur in the linked list based implementation, especially about the invariant that needs to be maintained with respect to the when the queue is full versus queue is empty, right? So we said that we have some fixed number of elements in the queue, and then we inserted and there are certain elements for 6 elements, and then we inserted one element at the back, so we need to keep track of the back pointer, and we also need to remove elements which requires us to maintain the front pointer. I'll switch off the video because I'm on low bandwidth again. So after that, the state of the queue looks like as shown in the third diagram, which is this. So front is pointing here and back is pointing to the last element, right? So that is our invariant that we are maintaining. In this case, although in the implementation qimpl.c, we are maintaining that back is pointing to the next element where the entry should be inserted. So it is pointing to 3 plus 1, I mean the entry of 3 plus 1. Okay, but let's continue with this, that front and back point to the first and last elements respectively. Now I perform these operations, remove, 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 and insert 1, 2, 3, 4, right? I would like you to draw what the state of the queue would be at this stage. For those of you who joined just now, the classwork is to write down the state of the queue after we have performed all these operations. Okay, Salman has written the state. If it is circular, sure, good. Yeah, so this is where the design decision comes into picture, whether you want to give an error if it is not circular, or you want to make it circular, and you might be able to accommodate these elements, right? So that is a design decision that we have to make. So let's follow Salman's suggestion that we'll make it circular. Now what is the state? Okay, so I'm not getting more responses. Okay, so let's check that. So let me see. So we have removed 3 elements, which means that I need to remove 2, 7, and 2, and therefore front will point to 9. And at this stage, I'm going to insert 1, 2, 3, and then 4, right? So that 4, the one that is shown currently on the screen as the first element, that is the previous 4. That is not the actual, the last 4 that is getting inserted. And back needs to point to one entry after that, right? So, and therefore we have to make it, so either we give an error saying that it's not circular, or saying that it is full, or we have to insert it in the circular manner, because there is space, right? So the advantage of circular queue using arrays is that there is space and you will be able to accommodate it. Alternatively, if you don't want to make it circular but still want to not waste space, then what will you do? The question is, if you do not want to make the queue circular, but you still want to take advantage of the whole space available, what will you do? Right. Uh, so as Salman says, we'll have to shift the elements, and that will change the complexities of insert and remove. And that might be acceptable, might not be acceptable. So that is going to be dependent on what you decide or what your manager decides, right? So, okay, so that should be understood. And therefore, what we will do is to do the circular list. So let's do a wraparound. We do an insert of 4, and therefore the queue is going to become something like this. Note that 4 and 9 are not consecutive. In memory, 3 and 4 are not consecutive, but logically they are consecutive. Right? In memory, 3 and 4, that is 1, 2, 3, and 4, are not consecutive, but logically they are actually consecutive. And we are still maintaining the invariant that front points to the first entry, back points to the last entry. So far, it was easy for us to figure out what was the size of the queue when it was not circular. We just do back minus front, and that would give us the size of the queue. Now, how will you find out the size of the queue? Any suggestions? Assuming that it is array of n size. Naimisha says n minus front minus back. That should work even in the case where front is smaller than back. Right. So does that work that way? Let me see. I think there is some small issue, because we said that initially front and back are the same, which is 0. And so front minus back will be 0, n minus 0 will be n. So MTQ will be specified as n elements. So I think there is some modification required, but I think Naimisha is on the right track. Any other suggestions? I know this is a little early in the day, and you have probably had quizzes this last week, but still, please wake up and try to work out. Okay, we'll come back to that question of how to find the size of the list. Let's do one more classwork, that I want to remove 5 elements and insert 2 elements. Insert element 2 in the queue. Please draw the array after this processing gets done. Shania says if front is less than back, then back minus front plus 1. Otherwise, n minus front plus back plus 1. Okay. Sure. Salman says 4 2 dot 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 3. Anish says same. Okay, I'll wait for a few seconds in case somebody else wants to try out. So when we remove 5 elements, 9, 5, 3, 1, 2 should get removed, and therefore front should point to 3, and when we insert 2, that should be inserted at the tail of the queue. So after 4 it should be added. Therefore 4 2 dot 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 3 seems to be the right answer. Okay, fine. So that is how it is going to look like. Now I am going to remove, and then the removal has to happen from the front, and therefore after removal, now front again points back to 4, and again we have this relationship between front and back where front is smaller than the back or less than equal to back. Right? So this part seems to be okay so far, and what is the non-triviality that comes up is kind of suggested by Naimisha's expression, right? So that is hinted by Naimisha's expression for finding the size of the queue. So let's understand that, and so I'm going to remove one more element now, and now front and back both. So since I'm removing it from the front moves ahead, and now front and back are both pointing to the element 2. Does this look okay? Are there any issues with this, whatever I'm showing on the screen? Okay. So Shania says, what happens to front and back if we remove 2? That's a good question. You guys suggest me what should happen if you try to remove 2. So removal has to happen from the back, and removal has to happen from the front, and therefore front should move ahead, and therefore front will start pointing to the next entry, and back will continue to point to where 2 was earlier. So I think Shania is asking the right question. What is the issue with whatever we are seeing currently on the screen with respect to the positions of front and back? Okay, so the invariant that we tried to maintain when the list was empty was when we said, let's see, so we said, did we do anything? Okay, we didn't say anything with respect to the, I think we did it in the code, but not here. Okay, so exactly the way Shania has said, I'm going to remove that element, and therefore back points where it was and front points to the entry next to it, right? Now what does this convey? Does this convey an empty list, or does this convey a list containing n elements, or a queue containing n elements? Okay, it does say that the queue is full, and we are not doing anything with respect to the entries. The entries might still be there. We are not setting those to some arbitrary values and so on, right? We are not setting those to int max or int min or something. So if you recall, when we said that front points to the first entry and back points to the last entry, and therefore if it's a circular queue, you might not be able to distinguish easily if the queue is full or empty. Right? I hope you are able to see that. Is there anybody who is facing trouble in understanding that queue being full versus queue being empty um is non-decipherable in the current implementation? Okay, I'm assuming that everybody is with me, and that we need to take care of in the other implementation, which we will look at after we go through the slides. So if the queue is empty, similar to what Shania had written, if front is greater than the back, right? So as we had on the previous slide, we'll have to have front equal to 0 and back equal to, let's say, I'm saying -1, but essentially that means the initialization, right? So initially back is pointing to the last element inserted, and therefore we will have to have the empty queue being defined as back equal to -1. Because that's the last entry. The next entry, as soon as it gets inserted, then front and back both are going to point to front equal to 0, back equal to 0. So therefore, after removal, before that, back should be pointing to -1. So queue implementation.c, which we saw yesterday, that was using front equal to 0, back equal to 0. Either of these could be used, but you have to be consistent with respect to this. So queue being empty on the previous slide, this cannot be just checked by saying that front is one ahead of back, right? So that cannot be used because that also signifies queue being full, right? So that is something which we'll have to worry about, and we'll come to queue implementation 2.c. So in our queue implementation.c, which was yesterday's, back points to the place where the next element should be inserted, and therefore we initialized back to 0. Whereas the implementation that we saw on the screen here, back points to the last element inserted, and therefore it should be initialized to -1. So both of these you should be able to understand, and you should be able to implement either way, right? Now write down the condition when the queue is full, right? So we have had a discussion on this so far, and before we look at the code, I would like you to write down what would be the condition when the queue is full. And that can't be the initialization, because initialization says that queue is empty. So please spend a few seconds trying this, then we'll come back to the code. For your benefit, I have moved it to the previous slide when the queue was empty. You can try inserting elements to make it full and see what happens with respect to front and back. But more importantly, you should understand this problem, that whatever is shown in the last state of the array, when the actual queue is empty, it can also be interpreted as queue is full, right? So that you have to understand first. Once you understand it, then you will be able to solve the problem. Abhishek says we can check full by maintaining a separate variable size. If size is 0 means it. That's a very good observation, right? So when you have insert and remove as separate API, you can do increment and decrement of another variable, and that can give you the size separately, right? So then you don't have to worry about the front and back relationship, because you have the size handy with you, right? So that's a very good way of implementing this. Anybody wants to avoid that variable and still see if you can do that with remove, with using only front and back? Okay, so let's discuss that part. So empty queue is this, the full queue is also the same, and although I have not shown elements, those elements exist there, right? So you cannot distinguish between the two. So one possibility is that we can leave one space unused. So we just insert n minus 1 elements, right? We never make, so therefore we will distinguish between the state where the full and the empty are going to be always distinguished, right? That is another. And as Abhishek has suggested, we could as well make uh, use of an additional size variable, the way we have used in qimpl.c, which can be used for tracking the size. Right? Murari says back and front will be adjacent, and both back and front will contain values, and also both adjacent to back and front will contain values. So Murari, it turns out that, I mean, you can take the example of integers, and if we allow arbitrary integers not using any -1 or int max, int min as sentinel values, then it becomes difficult to talk about the value adjacent to it, because all the values will be valid. So another possibility apart from these two is that we can use a sentinel value, right? That will also be in some sense leaving one space unused, but you could use that sentinel value as the end marker of the queue, right? So then back could always point to that sentinel, and that will probably indicate that you have full queue versus empty queue. That could be another way in which this can be done. Any other? Yeah. Yeah, I'll repeat this method on the slide. What I'm saying is that the end of the queue can always be marked with a sentinel, right? So that means that when the queue is empty, right, then you don't have that sentinel value. When the queue is empty, you don't have that sentinel value because the queue is empty. There is nothing like end of the queue. Right? The start and end of the queue is somewhere here. Right? So this entry is marked as sentinel, which means that it doesn't exist, right? So the sentinel doesn't exist. Whereas whenever you have some elements inserted, let's say you insert all these elements, then you cannot insert 9, and then you mark this as the sentinel, which indicates that it is going to be the end of the queue, right? So that is also in some sense leaving out one space unused, but sometimes it becomes easier to just look at the value rather than uh, leaving one space unused, right? So that requires us to probably keep track of what is the difference between front and back. If that difference is 1, I mean, and back is smaller than front, then we say that it is empty. But if the difference is 2 and back is smaller than the front, then we say that it is going to be full, right? So that is another way in which that can be done when we are using one space unused, right? But if you want to look at the value, then you can just read the value and say that, oh, this seems to be a special value, int min, int max, -1, whatever you want to use it, -319, whichever value you want to use, and that value will signify that is the end of the queue, whereas the empty queue will not have a sentinel value. That is another way in which that can be done. All right. So any other concerns, questions? Otherwise, we'll look at the second implementation, which implements the circular queue. The qimpl.c just gave an error when the queue was full, but this one should be able to handle the circular queue. Okay, so if there are no questions, I'll start presenting the code. Okay, so this is again, so far we have looked at C++, so I thought that as a change we'll look at C. Right? And it also indicates that you will be able to do everything in C, C++, whatever we are studying as part of this course. To enable wraparound and to make things manageable, I have defined the size of the queue, the size of the array to be 10 maximum. The queue is defined using the array front back, as well as we are maintaining the size, and that helps us distinguish between front and back, the empty and full. The initialization says that front and back are 0, which means that the invariant that we need to maintain is that back points to the next entry where the element should be inserted, the new element should be inserted. Insertion is going to require us this wraparound, right? So if the size is smaller than n, then there is no problem. You just go on inserting it at the back, increase the size. If, however, after the insertion, that is, if the size of the queue was n minus 1, it is going to become n now. And if that becomes n, that entry really doesn't exist, right? Because next time we are going to insert it at q arrow back. So since that array of n doesn't exist, or elements of n doesn't exist, we have to wrap it around, and therefore q arrow back will start pointing to 0. Again, this is possible that q arrow back equal to 0 and q arrow front is also 0 exactly at this stage, right? But size is going to distinguish between whether it is empty or full, right? So that becomes easy for us. Otherwise, I'm going to give you queue overflow error, which means that the size is already n, and therefore I cannot insert anything more, right? So that is always there with the array-based implementation. Any questions on the insertion? Okay, then I would like you to think about how will the queue removal look like, right? So I hope that the signature of queue removal is there on the screen. I would like you to spend a few seconds thinking about how would the array-based queue removal, queue element removal look like. So once again, we need to do queue arrow size minus minus. So that is definitely going to be there. But there are two cases to handle with respect to the front. We are removing from the front. So the front is going to move. If it moves to the right, of course it is going to move to the right, but the two cases are, one, it doesn't wrap around, and the second one is it does wrap around. So if I remove an element, if front is pointing to n minus 1th entry in the array, then it needs to wrap around to 0, right? So that is exactly in the same manner as the way we are talking about back in queue insert. We need to take care of front in queue removal. I'll wait for a few seconds and then we'll look at the code. Okay, so the code is exactly similar. Maybe I'll show you both the codes so that you can see the similarity. And that usually is a good indication that your operations on front and back are symmetric in some sense, right? So q arrow size is less than n. Similarly, q arrow size is greater than 0, right? So that becomes full versus empty. If that is the case, then we reduce the size because you cannot remove from an empty queue. and then q arrow elements of whatever is the front, that element I am going to return in E. Right? So that is the one that I'm going to return. And at that stage, if front becomes same as n, then I need to reset it to 0. Alternatively, you can avoid the condition by using mod n, and that will also give you the same value, right? QMT is Q arrow size. So currently we are using the size, but you can also play around with front, back, sentinel, whatever you want to use. And the printing is just printing it using the mod operator, right? So here is where the mod comes into picture, because front can be arbitrary. It need not be at 0. So front can be at arbitrary place, and then we might have to wrap around. So that uses the mod value, mod function. Okay. The main remains the same, and you also provide an empty queue. So you can try around playing around with this in different ways. I'll just run it for our discussion. So I'll show you. Yeah, so round 0 we try to insert 0 to 8, and then size becomes 9, front is 0 and back is 9, right? And after that, when I remove some 5 elements, size becomes 4, front is 5, back is 9, right? So these numbers are indicative, and you should try these out in a copy first yourself manually, and then look at this whether it matches, right? In the second round, these are probably happening in different orders. So in the second round, I'm trying to insert, since the size is 4, I can insert, let's say, 6 more elements because n equal to 10. And after that, there is an overflow of element insertion. And then at that stage, the size, the state of the queue is like this. Then I remove 5 elements again, and therefore the size of the queue becomes 5. At that time, when I try to insert elements again, I can insert 5 elements, but then the next few elements are going to incur a queue overflow, and so on, right? So you can try experimenting with this in a repeated manner. So that is what I have coded as different rounds. Right. Right. So the exact element that we are inserting is not important. What is important is the size. Therefore, we have not randomized what element we are inserting, but you can as well randomize that using the RAND function. So that is also okay. All right. Any questions so far?
Sir, I have a doubt outside. Okay, I'll just text it.
Yeah. Maybe there is an echo from my side, so I'll mute and you can still.
Okay, like I just had a general doubt, not regarding queues. This type def which we use at the start, if we have like type def int 1 and type def int element A and type def int element B. So yeah, so if both of them are ints, can we add 2 elements which are belonging to different types?
Yeah, so that's a good question. If we have 2 different types, when can we say that they are equivalent in some sense, or can you perform certain operations on them? So that is a little compiler dependent or compiler theory dependent, I would say. In case of C, C++, you will be able to add these 2, right? So there won't be any problem. So there is something called as name equivalence and structure equivalence, right? In some languages, it is structural equivalence, that whatever is the structure that is underlying these types, if that structure is the same, then you can perform operations on them, or they are equivalent, and then you can let's say relate them easily. In some other case, it is name based. What that means is that you can have the same structure. For example, you can have an integer e1 and integer e2, But these could be very different types. For example, one of them might be number of, let's say, cards in a deck, right? And the other integer might signify the number of computers in my office. Now there is no point, I mean, no point meaning in general there is practically these two should not be added. And therefore, although underlying structure is the same for both of them, some languages forbid you from performing operations on these structurally equivalent but naming wise different types. So in case of C++, this will work. So we follow the structural equivalence, so it's not really a problem. But since you asked this, I thought that I'll mention that there is name equivalence also, which requires us to have either same types, or those should be derived in case of inheritance from the same base type, and then they should be comparable, etc. Does that seem reasonable, Anish? Okay, great. Any other questions, concerns? Okay, so if there are no questions, then we will come back to our slide. That kind of completes our discussion on the queues, and I hope you will be able to implement a queue yourself using linked list based implementation or array based implementation. Although we have not really discussed linked list based implementation much, but it's not very different from what we have done with respect to the stack. In fact, it's going to be much easier with linked list rather than with arrays. But that array based implementation has that non-triviality, which I thought I'll highlight. So that's what I have done. So one practice problem for you is implement a stack using two queues, right? So you are not given a stack ADT, right? But you want to implement it. You want to create a stack ADT such that you have, and you have access to a queue ADT. Now using that, how will you implement the push and pop operations? So any suggestions on that? Any quick suggestions? Okay, so if you are worried about the complexity, yeah, at this stage, we'll say that we are not worrying about complexity. We are worrying about the functionality alone, because the complexity is going to go for a toss. So, but let's see if we are able to implement, let's say, push or enqueue operation using the stacks push operation. Sorry, the other way around. Which means that if I insert 1 to the stack, it should be at the top of the stack. That is okay. But when I insert 2, the next pop should remove 2, right? So if I insert 1 to 10, the first pop should remove 10, right? But you have access only to a queue, and you don't have, since it's an ADT, you don't have access to identify ith element in the array, etc. So that we don't have luxury of. So since there are no quick suggestions, I'll leave it as exercise. Can you implement a queue using 2 stacks? The other way around. That means 1, 2, 3, 4, 5 up to 10. If I insert and I remove, at that time I should be able to get 1 rather than 10, right? Because stack is going to use just push and pop operations. Can we implement 3 stacks using an array, that is without space wastage? 2 arrays is 2 stacks is okay, right? So you start from 2 different ends of the array, and that will give you 2 stacks using an array, right? But can you do 3? Right? So that is one question. Naimisha says, get into a stack and pop into other stack for queue implementation. Yes, that is the right approach. You'll have to build upon it, but yes, that is the right approach. And then in Visa's book, we have some practice problems at the end of chapter 3, or online also you should be able to perform some practice problems, let's say on CodeChef or Geeks for Geeks, Lead Code. Either of these should be all right. Okay, so that kind of completes our discussion on lists. We looked at the basic list, then stacks, queues, We implemented these using C or C++ with pointers or arrays. And we also looked at a little bit of applications. For example, for linked list, we looked at polynomials. For stack, we looked at, I think, balanced parentheses as well as prefix, postfix, infix. Then for queues, we looked at the call center application. Right. So that completes our discussion on lists. Any questions on this one? Otherwise, I'll quickly introduce trees. Okay, Murari says, while popping, insert all elements to a second stack and pop from second stack for all pops until second stack becomes empty. If in between push is there, then do it in stack one. Yes, that's a good approach. And those of you who are able to get past this first step of functionality, I would also recommend checking how the complexities of push and pop are going to be. Right? Earlier it was all order one with respect to our implementations, but now what will be the complexities, right? So that also please think about. Any other suggestions, questions, concerns? By the way, any feedback on what we could have done differently in the context of lists, which I can kind of incorporate in the further discussion on trees and so on. So trees we are going to look at for reasonably long time, considering that there are large number of different trees. So if there is any feedback, either you can give it now by email or send it via some representative. Any of it is fine. If you want to be anonymous, anything is okay. Okay, so let me start the Yeah, as a child, I used to hate when the teacher used to not leave the class early when the chapter finished and would start the next chapter. But yeah. Okay, Murari says, how to look at the worst time complexity in this case, 2 stacks for 1 queue. Right, so you have to think about it in terms of the number of elements in the stack at any point in time, and that way you will have to define the complexity. It's likely to be of the order of n in either way, but there are yeah, so I'll leave it at that. Yeah. So in the worst case, what can happen is that how many elements we are going to move from one place to another, that is one metric. The second one is how many NQs and DQs we are going to do, or pushes and pops we are going to do in the other example, in the other problem. So those are going to essentially define the complexity. So it could be 2n in the worst case, and therefore, depending upon your implementation, it can also be order, exactly order n rather than order 2n. But yeah, it will still be of the order of n.
Sir, just can we explain? Sorry, I think it's echoing.
Sorry, okay, let me mute myself.
Yeah, so we cannot say for every push and pop it will be n. So can we say for suppose n operations, can we average? Can we find the average time complexity in this case?
All right, so I think Murari has asked a rather interesting question. See, it is not always going to be order n for every push and pop, right? So sometimes it is going to be much smaller, maybe a constant also, right? Especially initially or when the stack size is small, it will have a very small constant number of operations. So a similar thing had happened when we did the maximum subsequence sum problem, where we said that maybe our analysis is not tight. Maybe the algorithm is tight, but our analysis is not tight. In that case, we have to probably do a more elaborate analysis using our algebraic expressions that, okay, the first insertion is going to take order, one, or maybe one push. The second will probably require either one push or one pop plus one push and so on. So all of this is going to be taken care of very explicitly, very carefully in a very fine-grained manner. And then we sum these up. And that is the tight analysis, which means that you are now modeling the complexity of each operation individually very, very carefully. We are not making a sweeping statement that, oh, in the worst case, it is going to be order n. We are just going to say that the first operation is going to require one operation. The second operation will require, let's say, two operations. The third one will require three, and so on. And based on that, then we identify what will be the complexity over, let's say, k such insertions. I will not use n, but let's say k such insertions, because we are talking about not insertions, operations, push or pop. So if that happens, then the complexity, if it turns out to be some function which is going to be quadratic in n, some function which is quadratic in n, then we say that over n operations, your complexity is order n square, and therefore for one operation, your complexity is, well, average complexity is going to be order n, right? So that is what Murari was suggesting, that can we say that it is going to be order n for, let's say, by averaging. It turns out that I didn't use the term worst case time complexity. I still use the term that average case time complexity. So these two are different. So if I say that order n square is the amount of time required for n operations, then I can say that the average time of one operation is order n. That doesn't mean that every operation is order n. It's still possible that some operation might still be order n square. But there are large number of operations which are, let's say, constant time or linear time, and therefore the overall complexity of n operations turned out to be order n square. But there could be one operation which is order n square, not in this particular example, but I'm talking in general. In that case, we should not say that the worst case time complexity of an operation is order n. We should still say that the average case is order n, because n square by n is n, but the worst case time complexity is decided by one operation's worst case time complexity, and therefore it will still be n square in that particular example. In this case, it so happens that either way you do, whether you perform a very fine-grained analysis or we try to identify more like an approximation, that okay, there are order n square operations, and therefore I divide it by n, and therefore my complexity is order n. That is what it will turn out to be. Sorry, I gave a little elaborate example, complexity analysis, but that is an important point. So there is a notion of amortized analysis, which we are not studying in this course. Those of you who are interested, you might be learning this in the algorithms course. Amortized analysis is actually worst case analysis, but it also deals with the average over multiple insertions. Let me give you an example, right? So let's say there is a kind of social network, right? And there are n number of nodes in this social network. Now, the operation that I'm doing is that for each node, and let me write that here, for each node I, for each neighbor of I, perform some order 1 operation, right? So that is my algorithm. Now, what will be the complexity of this algorithm, right? So this is typically going to be, okay, for each node I, and there are n nodes and m edges in this social network. So I'll say that the complexity of I loop is order n. Then for each neighbor, how many neighbors can a node have, right? Well, it could be connected to n minus 1 other nodes. So the complexity is order n minus 1, which is same as order n, and perform order 1 operation, and therefore the overall complexity of this computation will turn out to be order n square, right? So that is my analysis. And it's not wrong, it is correct that in the worst case you might require order n square analysis. But we also said that the original network has n nodes and m edges, right? M is not appearing anywhere. Now if you look at it closely, what essentially we are doing in these two for loops is going over each edge in the graph exactly once. What we are doing in these two loops is going over each edge in the graph exactly once, and therefore instead of saying order n square, I can say that the complexity of this processing is going to be order m. Now why is that order m important? Because m need not always be n square. You might have a very sparse graph, sparse network, where um, the overall number of edges might still be proportional to n. Does that mean that there is no node in the graph which has order n neighbors? No, we didn't say that. For example, there could be a node which might be connected to all other nodes in the graph, right? But we are saying that the number of edges is still bounded by m, and therefore the complexity of this code is still bounded by m. So that is where amortization comes into picture, where although our individual analysis of separate for loops was order n nested, therefore order n square, that is correct but not tight, right? So that is where amortized analysis helps us. Okay, I think that's an aside, and we have already exceeded the time, and you guys have succeeded in not making me start trees. So we'll start it tomorrow. Tomorrow it's Friday, so we will have the class at 11 o'clock. If there are any questions, we'll take those up now. Those who have classes, feel free to go ahead. What is the need of implementation of stack using queue? Does it relate to any real life application? No, it's more like a uh, fun exercise, I would say, right? So one of the important implications of this is coming from the fact that many times in companies you are just defining the public interface while designing the software. That public interface is your ADT. I mean, yeah, in some sense an ADT, and you are not allowed to go beyond that. So in some cases, you are forced to use those ADT and perform those operations. If those operations are not adhering to what exactly you want, of course, if you have good rapport with the other team, you will just ask them, "Arey yaar, ye function implement kar de," right? And then the person will probably oblige you by having that API added to the design. But not always this is possible. In that case, you are forced to use the APIs which are given to you. This particular exercise of implementing stack using queue or queue using stack essentially forces you to use those API and still implement a functionality. Right? So from a software engineering perspective, this is an important part. From the data structure perspective, it's not that important, but then it's a fun exercise. So I would still recommend think about it. You might not implement it, but try doing it in the pseudocode level at least. Naimisha says also regarding the question on how to differentiate empty full queue, can we set flags at few places? Like if we are setting a flag as a pointer which points to position 0 and initially flag arrow val equal to 0. If both flag is 0 and front equal to back, then empty queue. If flag is 1 and front equal to back, then full queue. That's also a good approach. You can do it like this. Can this flag be maintained? See the, yeah, I think this is possible to be done, because what we can do is that on removal we can reset the flag when the condition between front and back becomes this, and on insertion we can set the flag, because queue will become empty only on removal and queue will become full only on insertion. So I think this can be implemented and this will work. Anish says Sentinel is something like a flag. Yes, it is like a flag, but yeah, it is like a flag. But the way I was explaining it was more using a separate element. What Naimisha is suggesting is that you just keep track of a flag. Either way should be okay. There are finer details which are different, but otherwise, yeah, you can possibly categorize them into similar buckets. But yeah, I think these are definitely different ways in which it can be implemented. Good. Any other concerns, questions, suggestions? So there is a small difference between this and Sentinel, and that is, in case of Sentinel, we typically lose a value, right? So if there is a range of integers which I want to support, typically I'll give away one value which can be used as a Sentinel. Whereas in this case, you will not lose that value. It's like maintaining size in some way, where the size is being maintained as not 0 to n minus 1, but it's mentioned as empty versus full, right? So that is in some sense. Oh, am I not audible? Okay. Anyway, in case I am not audible, the class is over. So we can log out, and we'll meet tomorrow at 11. See you. No, tomorrow is Friday timetable according to the calendar. So we'll have to meet at 11. I'll just paste the link. So this shows that it is a Friday timetable. Okay, so we'll stop here.